For more than a century, black holes have occupied a unique place in human thought. They are not merely astronomical objects. They are symbols of mystery, of the unknown, and of the terrifying power hidden within the universe. Ask almost anyone what a black hole is, and they will likely give the same answer: a region of space where gravity becomes so strong that nothing can escape. Not matter, not radiation, not even light itself. Simple, elegant, settled, or so it seems. Because beneath that familiar explanation lies one of the most controversial questions in modern astrophysics. A question that touches not only black holes themselves, but the very foundations of our understanding of reality. What if black holes are not what we think they are? What if the most famous objects in modern astronomy conceal a deeper problem, one that has been hiding in plain sight for over 100 years? To understand why some physicists ask these questions, we must first understand how black holes entered science in the first place. The story begins in 1915, when Albert Einstein published General Relativity. At the time, it was nothing short of revolutionary. For centuries, gravity had been understood through Newton's laws. Objects attracted each other across space. The sun pulled on the Earth pulled on the moon. Einstein changed the picture entirely. Gravity was not a force. Gravity was geometry. Matter and energy curved space-time itself, and planets were not being pulled through space, but were following the natural curves created by massive objects. The idea was almost absurd, yet observation confirmed it. The orbit of Mercury, the bending of starlight, time dilation. General relativity worked, and it worked brilliantly. But almost immediately, Einstein's equations revealed something unexpected. A German physicist named Karl Schwarzschild found an exact solution to Einstein's equations while serving on the Eastern Front during the First World War. His solution described what would happen if a sufficiently large amount of mass were compressed into a sufficiently small volume. The result was extraordinary. Space-time itself appeared to fold inward, and a boundary emerged, a point of no return. Today we call it the event horizon. At first, few people believed such an object could exist in nature. It seemed like a mathematical curiosity, an artifact of the equations, a strange possibility with little connection to reality. Even Einstein himself remained skeptical. Yet, as the decades passed, something remarkable happened. Astronomy advanced, new observations arrived, and physicists realized that under certain conditions, gravity could become overwhelmingly dominant. When a massive star exhausts its nuclear fuel, the outward pressure generated by fusion begins to disappear. For millions of years, fusion had acted as a counterweight against gravity, but eventually the fuel runs out, the balance breaks, and gravity wins. The star collapses. The more physicists studied this process, the more troubling the conclusion became. For sufficiently massive stars, nothing seemed capable of stopping the collapse. No known force, no known pressure, no known mechanism. The star simply continued inward, smaller, denser, hotter, and more compact, until, according to the equations, a black hole formed. As the 20th century progressed, black holes transformed from theoretical oddities into central actors in modern astrophysics. By the 1960s and 1970s, evidence was accumulating everywhere. Quasars, X-ray sources, compact objects, and invisible masses affecting nearby stars. Eventually, supermassive black holes became the preferred explanation for the enormous engines powering active galaxies. And today, astronomers believe that nearly every large galaxy contains one, including our own Milky Way. At the center of our galaxy lies Sagittarius A star, an invisible object containing roughly 4 million times the mass of the Sun. At the center of galaxy M87 lies an even larger monster, billions of solar masses concentrated into a tiny region of space. In 2019, the Event Horizon Telescope collaboration released what many called the first photograph of a black hole, and the image spread around the world, appearing on front pages, television broadcasts, and science magazines. For many people, the debate seemed over. Black holes had been photographed. The case was closed. But science is rarely that simple, because while black holes became increasingly accepted, a profound problem never disappeared, in fact. It sat quietly at the very center of the theory itself, the singularity. For most people, the event horizon receives all the attention, but physicists are often far more interested in what lies beyond it. According to classical general relativity, the collapse does not stop. Matter continues inward, density increases, curvature increases, gravity intensifies, and eventually the mathematics predicts something extraordinary. A singularity, a point where density becomes infinite, where space-time curvature becomes infinite, and where the equations themselves cease to function. This is where things become uncomfortable, because infinity occupies a strange position in science. Mathematicians work with infinity all the time, but physicists tend to become nervous whenever infinity appears inside a physical theory. History has taught them caution. Again and again, infinities have signaled that a model is incomplete, that something deeper remains undiscovered. Consider a simple analogy. Imagine a map that helps you navigate a city. The roads are accurate, the landmarks are accurate, and the directions are useful. But eventually, you reach the edge of the paper. The map simply ends while the city continues. The edge is not part of reality. It is a limitation of the representation. Many physicists see singularities in a similar way, not as physical objects, but as indicators that a theory has reached the edge of its applicability. And black holes contain perhaps the most famous singularities in all of science. This creates a dilemma. On one hand, general relativity has passed every major experimental test thrown at it, with astonishingly accurate predictions. On the other hand, its most extreme prediction appears to lead directly into mathematical absurdity. Infinite density, infinite curvature, infinite gravity. These are not merely large numbers, they are signals that something unusual is happening. Then came quantum mechanics, the second great revolution of 20th century physics. Quantum theory successfully explained the microscopic world, atoms, particles, radiation, and fields, and became one of the most successful scientific frameworks ever created. Yet, there was a problem. General relativity and quantum mechanics refused to cooperate. Each worked beautifully in its own domain, yet when pushed together under extreme conditions, contradictions emerged, and nowhere were those contradictions more severe than inside black holes. Suddenly, singularities were no longer the only problem, because another paradox appeared, one that would occupy some of the brightest minds in modern physics: the information paradox. According to quantum theory, information cannot simply disappear from the universe, yet according to certain interpretations of black holes, information appears to be destroyed forever. Stephen Hawking spent decades wrestling with this issue. Entire generations of physicists joined the effort, books were written, conferences organized, and thousands of papers published. And despite enormous progress, complete consensus never emerged, which raises a fascinating question. If black holes are among the most studied objects in modern physics, why do so many fundamental questions remain unresolved? Why do singularities still exist? Why do paradoxes persist? And perhaps most importantly, what if the singularity itself is the clue? What if the problem is not hidden inside the black hole, but hidden inside our assumptions about what happens during collapse? This is precisely where a small number of physicists begin to diverge from the mainstream picture. Among them, French astrophysicist Jean-Pierre Petit, who argues that the true mystery may not be the black hole itself, but why we ever accepted the singularity in the first place. Jean-Pierre Petit is not interested in proving that gravity does not exist, and he is not trying to overthrow Einstein. In fact, one of the most misunderstood aspects of his work is that he accepts much of modern physics. The disagreement begins somewhere else, at the exact moment where physics predicts infinity. To Petit, that is where alarm bells should start ringing, because throughout the history of science, infinities have rarely survived for long. They usually indicate that a model has been pushed beyond its natural limits. For most physicists, the singularity is treated as a consequence of gravitational collapse. Matter falls inward, pressure becomes insufficient, collapse continues, and eventually the equations predict an infinitely dense point. But Petit asks a different question. What if collapse never reaches that stage? What if nature itself prevents the formation of a singularity? At first, this might sound like a minor distinction, a technical disagreement between specialists, but the consequences are enormous. If the singularity never forms, then much of the conceptual baggage surrounding black holes begins to change. The information paradox changes, the interior structure changes, the final fate of collapsing matter changes, and perhaps most importantly, the object itself changes. Instead of a black hole, Petit proposes something he calls a plug star. To understand the idea, imagine a massive star dying, fusion stops, gravity begins crushing the star inward, the collapse accelerates, and the star becomes denser and denser. According to the standard picture, there comes a point where nothing can stop the process, an event horizon forms, and the singularity eventually follows. But Petit argues that another mechanism may appear before that final stage is reached, a mechanism capable of resisting complete collapse. Not enough to return the star to normal, not enough to reverse gravity, but enough to prevent infinity. In his view, nature does not allow the journey to continue indefinitely. Instead, the collapse reaches a limit, a kind of physical stopping point, a plug. The star remains incredibly compact, incredibly massive, and incredibly dense, but it never collapses into an infinitely small point. The singularity never appears. Hence, the name, plug star. The collapse is plugged before physics breaks down. Now here is where things become truly fascinating. Most people imagine that if a plug star existed, it would look dramatically different from a black hole. But according to Petit, the opposite may be true. From a distance, a plug star could be almost impossible to distinguish from a black hole. Matter would still fall toward it, gas would still heat up, accretion disks would still glow, nearby stars would still orbit an invisible mass, and jets could still emerge. To a telescope observing from thousands or millions of light years away, the object might appear nearly identical. And this creates a profound scientific challenge, because if two models explain the same observations, how do we determine which one is correct? This is not a new problem in science. History is filled with examples where multiple theories explained the same data, and eventually new observations revealed subtle differences. One model survived while the other disappeared. Petit believes that black holes and plug stars may represent a similar situation. The observations themselves are not necessarily wrong. The interpretation may be. And that distinction is crucial, because many people assume that the image of M87 released by the Event Horizon Telescope settled the question forever. But what exactly did the telescope observe? It did not photograph a singularity. It did not photograph the interior of a black hole. It observed radiation surrounding an extremely compact object. An extraordinary achievement, a historic accomplishment, but still an observation of the environment surrounding the object, not direct evidence of an infinite density singularity. Petit repeatedly returns to this point. Observations prove the existence of extremely compact, massive objects, but what remains open to debate is the nature of those objects. Are they black holes, or are they something else? This distinction may seem subtle, yet it lies at the center of the entire discussion because the singularity itself remains forever hidden behind the event horizon. By definition, it cannot be directly observed, and that means physicists are forced to rely on models, interpretations, and theoretical frameworks. Whenever interpretation enters the picture, disagreement becomes possible. But perhaps the most interesting aspect of the plug star is not what it explains. It is what it removes. Imagine for a moment that Petit is correct and that no singularities exist anywhere in the universe. Immediately, one of the strangest features of black hole physics disappears. No infinite density, no infinite curvature, no infinite gravity. The laws of physics remain finite, continuous, and physical. Many researchers find this idea attractive, not because it has been proven, but because infinities have always made physicists uncomfortable. The dream of physics has always been to describe reality using finite, understandable laws, and whenever infinities appear, they often signal missing physics, missing information, and missing understanding. This is precisely why singularities remain controversial even among physicists who fully accept black holes. Most do not actually believe that infinity represents a literal physical object. They view it as evidence that general relativity eventually requires modification, perhaps through quantum gravity, perhaps through an entirely new framework, perhaps through something not yet discovered. Petit simply takes the argument one step further. Instead of waiting for quantum gravity to eliminate the singularity, he proposes that the singularity never forms at all. And this brings us to a deeper philosophical question. What is the purpose of a scientific model? Is it enough for a model to fit observations, or should it also remain conceptually coherent? Imagine two maps of the same territory, both guiding you successfully, both predicting the location of cities, both helping travelers reach their destinations. Yet one map contains impossible geometries, infinite roads, infinite intersections, infinite distances. Wouldn't you naturally suspect that something was wrong with that map? This is essentially the intuition behind the plug star. Not that black holes fail observationally, but that singularities represent a warning sign, a clue that the map may contain impossible features. Of course, critics of Petit immediately raise an obvious objection. If plug stars exist, where is the evidence? This is a fair question because science cannot operate on philosophical elegance alone. Observations matter, predictions matter, and data matters. Any alternative model must eventually confront reality, and this is precisely where the debate remains unresolved. The challenge is that extremely compact objects are extraordinarily difficult to study directly. Even the most advanced instruments currently available observe only their surroundings, and the closer we get to the event horizon, the harder the problem becomes. Future observatories may change that. Future gravitational wave detectors may reveal subtle differences, and future imaging techniques may uncover signatures that distinguish black holes from alternative compact objects. Or they may confirm the standard picture beyond reasonable doubt. Nobody knows. And that uncertainty is what makes the debate so interesting, because science is strongest not when questions disappear, but when important questions remain open. Yet there is another reason why Petit continues to challenge the conventional picture, one connected to his broader cosmological work. In his view, the black hole problem is not isolated. It is connected to a much larger issue, the accumulation of anomalies within modern cosmology. Dark matter, dark energy, singularities, various theoretical patches added over decades to preserve the standard framework. Petit believes these problems may share a common origin, a deeper misunderstanding about the structure of the universe itself. And that belief eventually leads him toward his Janus cosmological model, a model that attempts to explain some of the biggest mysteries in modern physics from an entirely different perspective. And that is where our journey will continue. In the next video, we will explore the Janus cosmological model and the extraordinary questions it raises about the nature of reality itself.